Okay, so our first example of solving one of these second order equations using a power series is this one. We want to find two power series solutions about the ordinary point x equals 0 for y double prime plus x squared y equals 0. Okay, so what we're going to do is assume that our solution takes the form y equals the sum from n equals 0 to infinity of Cn x to the n. This is a power series centered at 0, which is the ordinary point that we're being asked to use. And now we need a second derivative, y double prime. Okay, so what would y double prime look like? Well, it's the power rule applied twice to this general term in here. And remember, if I apply the second derivative to this guy, this power series will have a constant term as well as an x term, and the second derivative will get rid of both of those. They both become zeros by the time I take their second derivative. So really, actually, instead of starting at term 0 now, we're going to be starting at term 2, n equals 2 to infinity. And then my power rule applied twice will give me a term that looks like this. Okay? You should be able to verify that without too much trouble. Okay? And in other examples, we'll do y, y prime, and y double prime, but we don't need y prime for this dE. It doesn't show up anywhere. So now what I want to do is take the y and the y prime that I have here and substitute those in directly to my dE. So this is going to look like my sum from n equals 2 to infinity of n times n minus 1 times, I forgot my Cn in here, didn't I? So there should be a Cn in there. Cn x to the n minus 2 plus x squared times y, which is the original power series. Sum from n equals 0 to infinity, Cn x to the n. Okay? I can multiply, this is equal to 0, but we'll set that equal to 0 at the very end. What I want to do now is try and combine all of this into a single summation, set that equal to 0 because that's what my dE says is happening, and then kind of proceed like we did at the end of the last section when we did a similar example. I can multiply this x squared into this sum right here. So this becomes summation where we go from n equals 2 to infinity, n minus 1, Cn x to the n minus 2, plus the sum from n equals 0 to infinity of the x squared in here is going to make that x to the n plus 2. So I get Cn x to the n plus 2. Okay, and now what we have are two different series that we want to combine into one by adding them. And as we saw back in the previous section, 6.1, there's two things that need to be in place for us to do that. First of all, these x terms, these factors of x to a power showing up in each of these little formulas, needs to be initiated in the same place. So, for example, what does the first term look like in this series? And ignore the coefficient, we really only care about the power on that x. Plugging a 2 in for the n here gives me x to the 0 power. So this guy starts at x to the 0 power. Over here, we initiate this series by plugging 0 in for n. 0 plus 2 is 2. So this guy starts at x squared. So here's what that means. This series is going to have a constant term corresponding to x to the 0 and an x term corresponding to x to the first power, which this series will not have. So this series is going to have two terms that aren't going to be able to combine with anything in this series. And the way that we deal with that is we pull those two terms out of this series and write that this way. So let's think, what would the constant term look like? I'm plugging a 2 in. 2 times 1 times C2. That would look like 2C2. X to the 0 power, so just that. It's just my constant term. Then I plug n equals 3 in, and I'm going to get 3 times 2, which is 6, C3, and then x to the 3 minus 2, or x to the 1, or just the x power. The next term in that power series would be an x squared term, which is where this series starts. So now I'm getting into territory where the terms of this series will combine with the terms of this series, and I don't need to pull anything else out. However, by pulling the first two terms of this series out, we are now at n equals 4. We've dealt with n equals 2 and n equals 3, and now we're at n equals 4 here. Okay? N times n minus 1, Cn x to the n minus 2 plus this guy, n equals 0 to infinity, Cn x to the n plus 2. So now both of these series will start at an x squared term. And you can check that. Plug a 4 in, I get an x squared here. Plug a 0 in, I'm still getting an x squared there. So that's the first thing that needed to take place. But the second thing is that we need both series to have the same starting value for n. Okay, and in order to make them have the same starting value, we make some kind of a substitution. So what I'm going to do is try and turn this n equals 4 into an n equals 0. So these two terms look the same as they were before, 2c2 plus 6c3x plus, and then I would like this series to start at n equals 0, going from 0 to infinity. And remember how this works. When we re-index a series, I subtracted 4 from my first value for my index. So anywhere I see an n, which happens in 4 places here, I'm going to replace it with an n plus 4 to compensate. So that n becomes n plus 4. N plus 4 minus 1 is n plus 3. This becomes c n plus 4, and this becomes x to the n plus 4 minus 2, which is n plus 2. Okay? Plus n equals 0 to infinity, cn x to the n plus 2. And you can see now that I have an x to the n plus 2 showing up in both series. All right? So now we're equipped, we're ready to combine these two things. And one thing you should do, I'm not going to do this every time, but one thing you should do when you re-index a series is you should just check to make sure that the first term of this series is the same as the first term of this series. So plugging a 4 in here gives me 4 times 3 c4 x squared. Do I get the same thing here? If I plug a 0 in, plugging a 0 in here gives me 4 times 3 times c4 times x squared. Same first term as that. So it's helpful to do a little mental check just to make sure you didn't make a mistake when re-indexing like that. Okay, finally we've got this 2c2 plus 6c3x plus the sum from n equals 0 to infinity, and now we can combine these. So I get n plus 4 times n plus 3 cn plus 4 plus cn, and that's the coefficient on that x to the n plus 2 power, and now we set that equal to 0 because that's what's happening with our DE. It's homogeneous. So this is where we want to use our identity property. Remember, we have a constant term here, an x term here, and then in this series we have x squared, x cubed, x to the 4th, all the other terms. And the identity property says that if this entire series is identically equal to 0, then all of the coefficients need to equal 0. Notice here that's going to automatically imply that both C2 and C3 are equal to 0. We've lost C0 and C1 in this process. Okay, so C1 and C0, or C0 and C1, those are gone. But that's okay because those are going to turn into our parameters. So here's what we're going to do. C0, we're just going to continue calling that C0. Okay, C1, we're going to continue calling that C1. C2, by the identity property, we're saying has to equal 0, as is C3. From here forward, determining the remaining coefficients requires us to use a recurrence relation, and that's where we go to this guy. This, in square brackets, is the coefficient on my x term that's showing up in that formula, and that has to equal 0 for every term by that identity property. So we're going to pull that out, n plus 4 times n plus 3 cn plus 4 plus cn equals 0, and that implies that cn plus 4 is equal to negative cn over n plus 4 times n plus 3. Okay, solved for cn plus 4 there. This is my recurrence relation. All right, so notice if I plug a 0 in for n, that gives me C4, which is my next term that I need. So what I'm going to do is from here forward, I'm going to keep track of what value I'm using for n. n equals 0 is going to give me C4. C4 is going to equal negative C0. Again, that's what n is, so negative C0 over, plugging 0 in for n's, my n's here, 4 times 3. Which I'll just write as 4 times 3, okay? And now I'm going to continue working out a whole bunch of coefficients here, and the goal is to see if, I can get enough terms to get an idea of what's happening with this series. So let's plug a 1 in. That's going to give me C5, which is equal to negative C1. There's my recurrence relation right there, so negative C1 over, plugging a 1 in, 5 times 4. And actually, that's enough. So C1 is just C1. There's no substitution to be made for either of these, C0 or C1s. n equals 2, what happens there? For n equals 2, I'm going to get C6 equals negative C2 over 6 times 5. You should start to see some patterns here that you can use to come up with the remaining coefficients without having to keep looking at your recurrence relation. C2, we've showed up here is equal to 0. So this whole thing actually just becomes 0. What happens at n equals 3? That gives me C7, which is negative C3 over 7 times 6. But C3 was also equal to 0. And so that term zeroes out. What happens at n equals 4? I get C8, which equals negative C4 over 8 times 7. And here, C4, we have already found up here. It's equal to negative C0 over 4 times 3. That's the same thing as, notice I have a negative here appearing here, so that's going to be a positive C0 over the 8 times 7 here. And then I get this denominator, which will be brought down into this denominator, giving me times 4 times 3. We're going to get a few more terms here. N equals 5 gives me C9, which is equal to negative C5 over 9 times 8. C5 we found up here. Negative C1 is going to give me C1 over 9 times 8 times the denominator up here, which was 5 times 4. Okay, those top values are going to go off screen a little bit, but that's okay. In fact, I'm going to go all the way down to n equals 9 here. So this is going to give me C10, which equals negative C6 over 10 times 9. C6 we found was equal to 0. So this whole thing goes to 0. In fact, we can also say that C11 will also go to 0 because C11, when I plug that into my recurrence relation, I'm going to get a C7 up here, which was equal to 0 as well. So one pattern you should see emerging is starting from C4, we have 2 non-zero terms followed by 2 zeros, followed by 2 non-zero terms, followed by 2 zeros. If we let that pattern continue, we don't have to, every time we encounter those 2 zero terms, we can just automatically say equals 0 instead of going back to our recurrence relation. N equals 8 gives me C12, which is equal to negative C8 over 12 times 11. C8 we found up here. This will give me negative C0 over 12 times 11 times 8 times 7 times 4 times 3. It's getting very messy down there. And notice I'm not doing all that multiplication. Like we've said previously, it's actually better, not all the time. Our last example in this section, we actually will do the arithmetic And we'll talk about that when we get to it. But for the most part, if we get these big products, it's better to just leave them as products because it reveals a pattern that's useful. C13 is going to be negative C9 over 13 times 12, which equals negative, so finding C9, that's up here, that was equal to C1, and that's over 13 times 12 times 9 times 8 times 5 times 4, okay? Now, our goal here is not to find a general solution, but we're doing enough work to find one. It's saying it wants us to find two power series solutions to about the ordinary point x equals 0 for that dE. Now the way we're going to find these two series solutions is we're going to remember what we just found. These are all coefficients on our power series that we defined up here. So each Cn is a coefficient on an x to the n term, right? So with that in mind, this is telling me that my constant term is C0 or C0. My coefficient on my x term is C1. The coefficients on my x squared and x cubed terms are both zeros, so those terms are going to go away. And then I have this guy, negative C0 over 4 times 3, and that'll be x to the 4th power there. That's the coefficient on my x to the 4th power. So I can build this series out of these coefficients, putting them where they belong. But not only that, if you look at the unknowns that are left, C0 and C1, those are the only unknowns left in the whole thing. C0 and C1 appear in a recurring sort of pattern here. Here's a C0 and a C1, C0 and C1, so on and so forth. What I'm going to do is get these two solutions by thinking of the fact that these are parameters, right? The C0 and C1 are parameters, which means I can assign any value that I want to those. So I'm going to start by assigning a 1 to C0. C0 equals 1. And I'm going to assign, a 0 to C1. Okay, what that means is that all of the coefficients that we just found that have a C1 in them are going to become zeros, and then all of the C0s are going to be replaced by 1s. And so that gives me the following solution to my dE. Let's find all the C0s. So I'm going to have a C0 here, which is equal to 1. I have another C0 right here, which is equal to minus 1 over 4 times 3. Now remember, that's C4, which was my x to the 4th term. And then I'm going to go down to the next C0 that appears, which is down here. It's my C8, and that's going to look like plus 1 over 8 times 7 times 4 times 3 x to the 8th. And then I have one more C0 term showing up way down here. Plugging a 1 in for that is going to give me minus, this is barely going to fit, 1 over, where were you? There you go. 12 times 11 times 8 times 7 times 4 times 3 x to the 12th plus dot dot dot. Okay, so that's one solution to this dE, and I did it by putting a 0 in for C1 and a 1 in for C0. If I do the reverse of that, if I assign C0 equals 0 and C1 equals 1, what that's going to do is make all of my coefficients that have a C0 and them go to 0, and I'm only going to be left with the coefficients involving a C1 somehow. That C1 will equal 1, and so that I get this. Y2 equals, let's see, C1, remember that's the coefficient on my x term, so that's going to just be 1x or x. C1 here, or this C1 appears in the C5 coefficient, so this becomes minus 1 over 5 times 4 x to the 5th. Then my next C1 appears down here in my C9 coefficient, so that's going to be plus 1 over 9 times 8 times 5 times 4 x to the 9th minus, my next C1 term shows up down here. There's where the minus is coming from. 1 over, let's see if I can squeeze that in, 13 times 12 times 9 times 8 times 5 times 4, and that's x to the 13th power, okay? Plus dot, dot, dot. So these two guys right here are the two solutions that we're being asked to find. And based on that theorem that we're not proving, but we are going to be using, these are linearly independent as well. So that means that these two power series together form a fundamental set of solutions for this DE. So even though the problem didn't ask for it, I could use those to write the general solution. My general solution would look like y equals c naught times that first series, y1, plus c1 times the second series, y2. Now I'm writing it in this form because I don't want to write these entire series out again, but if I wanted to put it in that form, I would take the y1 that I just found, put it here, the y2 that I just found, and put it there, and that is now the general solution for this homogeneous equation. Okay, as you can see, these are lengthy problems. There's a lot of work that goes into these. And they all kind of have the same pattern. So we're going to do a couple more examples, but we're going to save those for the next videos.